Hello, my name is Elena Arseneva. I'm from St. Petersburg, Russia, and I would like to talk to you about our result at Welcome, which is on an upward point set embeddings of paths and trees. And first of all, this is a joint work with a great team of people. Here are the photos. From left to right, it's Pilar, Cano, Kleist, Tamara, Mchedlidze, Saeed, Mehrabi, Irene, Parada, Pavel, Valtr, and below you see myself. So let's start. Okay, so suppose you have a planar graph G, which is a set of vertices and a set of edges, pairs of vertices, and the planar embedding of G is a mapping from the set of vertices V to points in the plane, so that edges of the graph are mapped to some curves that connect their endpoints, and the embedding is a planar because and when there are no crossings between the images of the edges. Okay, so if we are talking about straight line, planar straight line embedding, then all the curves should be straight line segments between the respective points. And there is a famous theorem named Far's theorem that every planar graph has a planar straight line embedding. So, meaning that if you can draw a graph without crossings with curved edges, then you can draw it with straight line edges as well. What is upward embedding? So now consider directed graphs. All the edges are now have directions, and a planar straight line embedding of that graph is an upward planar straight line if every edge points upwards, meaning that its first endpoint is lower than its last endpoint. Yeah, here you can see an example. Can there be some type of Far's theorem concerning such type of embedding? Well, of course, you do not need to have cycles in your graph, otherwise you cannot have a respective partial order and you cannot embed it with all the edges pointing upwards. So even then, if I give you some directed acyclic graph, which is planar, can it have upward straight line embedding? Well, it turns out that that's not the case. So here are a couple of examples. So these graphs are planar and acyclic, but they cannot be embedded as we want. However, if your graph is a tree, then this is still the case. What we consider in this work is a more specific question. If I give you a graph and a point set, can you find such a matching between the vertices and maybe a part of the point set? Because the size of this point set can be bigger than the size of the vertex set of the graph. So can you find such a mapping which would produce an upward straight line embedding? So of course distinct vertices of the graph should be mapped to distinct points of our point set. We call a point set general point set if there are no 3 points on the same height. Given a graph and a point set, it is NP complete to decide whether there is a upward straight line embedding of that graph on that point set. Now, if we restrict our graphs considerably to be paths, meaning that you have a path and each edge you can direct either way, right? So it's directed path. Then in some cases, it is shown that there are upward straight line embeddings. Like if the point set is convex, then any path can be embedded. If the graph is, on the other hand, more restricted, so it's not only the path, but it has 5 switches. By switches, I mean the turning points. So you have monotone chunks of edges which are directed the same way, and then there are edges directed the other way. So the switch between the directions is what I call switch, and one maximal monotone chunk of edges I call section, right? You have at most 5 switches, at least 2 sections of length, at most 2, and then you can embed it. The third type is also a very restrictive case, when you can have as many sections as you want, but all the upward sections, all the odd sections, say, are of length 1, just 1 edge. Then you can embed it. Then, not only paths are considered, but also caterpillar graphs. Caterpillar is a tree where if you delete all the vertices of degree 1, then you receive a path, and that path is called a backbone. So if you have a caterpillar, we still can embed it in any convex point set. There is a tree and a convex point set, such that this tree cannot be embedded on that. So for trees, it's already not the case that it can be embedded. There is a counterexample. And the last thing which is considered along this line of research is, what if I give you more points than vertices in the graph? So then a path with k sections can be embedded in a larger point set. So here the set is not necessarily convex, it's just a general point set. Okay, so this is the state of the art. This might not be a comprehensive list of all the results, but I didn't want to spend more time on this. And here's what we did. We did several steps advancing this state of art. So first of all, we gave another NP completeness proof for a different problem actually. Previously, the graph might have had cycles. Now we consider only trees. However, we fix one vertex. So we say that here's the tree, here's the point set, and one vertex, the specific vertex of a tree, should go to the specific vertex of a point set. And then we prove that if we fix one vertex and we have a general point set and a tree, the problem is NP complete. Our second result is a positive one. We just enlarge the family of paths that admit our upward straight line embedding. See, like if our point set is not convex, beforehand we had several results for paths, but there were many restrictions, very restrictive cases in the length of sections. So in both cases, there must be sections of length 1 or of length at most 2. Here we consider lifting this restriction, and we take one first step towards this. So we consider only 3 sections, but then all the sections, each section can be of any length. as long as the middle one is long enough. It should be longer than each of the other ones. We also advanced our result on caterpillars. So suppose you have a caterpillar backbone of k sections, and you have a size point set of size v times 2 to the power of k minus 2. Then you can embed your caterpillar. And finally, we considered counting the different embeddings. One-sided convex point set, which is a y-monotone convex point set. If you have a path of k sections, then the number of different upward point set embeddings of your path is k. Okay. Therefore, our results. And let me just illustrate a couple of them. So first of all, NP hardness. Again, we have a tree, a directed tree, a point set of the same cardinality as the set of vertices of our tree, a vertex, a fixed vertex S of our tree, and a fixed point P of our point set. And the question is there upward point straight line embedding of our tree T on the set S such that the point S is the vertex S is mapped to the point P. And we prove that this is NP-hard by reducing from three partition. Three partition is the following problem. We have a multiset of 3m integers. Thus there exists a partition into m tuples of each of size 3, so that for each tuple, if we sum up the numbers, we will get the same number, b. Okay, and here is our reduction. So we are given an instance of the three partition problem, and we build a tree this way. So we have a vertex S and then several branches. So it's actually a star if you don't regard the directions. So we have large branches and small branches. Large branches are these red branches here, and each of them has two edges upwards of one direction and L edges of the other direction, where L is greater than the sum of all the numbers. And the small branches represent the numbers that are given to us, the 3m integer numbers. So there are 3m small branches and 3m plus 1 large branches. And the point set is as follows. So we have a point P, which is the lowest point of our point set, and two convex curves where we place the small sets and the large sets. So you can see the zoomed version. So we just separate the area by the sectors emanating from P, and then alternatingly we take points on the further curve, on the upper curve, and on the lower curve. The difficulty in the proof is to prove that if we want to embed a tree built this way to the point set built this way, such that S goes to P, if you can embed, then you can also embed it nicely. And nicely means that all the large branches of the tree go to the green parts one by one, and all the small branches go to the orange parts. And if we manage to do that, we separated each orange branch between the two green branches, which means that we exactly found the partition. If we want to collect all the points, we will need to have 3 small branches there in every orange point set. And this will correspond exactly to the partition. The other result I wanted to briefly talk about is the algorithm for embedding a path. So again, we have a path of 3 sections, such that the middle section is longer than the other 2. So we consider a line going through B and T, the bottommost point and the topmost point of our point set, and the half planes that correspond to that line. And then if one of the half planes encloses enough points, meaning that the total of both branches, both first and third branches, then it's the left case, and otherwise it's the right case. So in the left case, then we want this large half plane to contain the 2 branches, and if there are more than what we want, then we rotate a ray emanating from B, from the bottommost point, so that it sweeps enough points. So in the end, we have a partition of our space, of our plane, into 3 convex regions, and every branch of our path will go to its own convex region. Then if we have a convex region, this means that no edges can cross, of course, if they connect points within one region. And in one region, we need to just do a monotone subpath, and monotone subpath is very simple. You just sort the points and connect them in order. Okay, so here the situation is a little bit different because we sweep not from the ray from B, but with the ray from T. Okay, so in summary, I just show you again the slide with all the results and our results. So in 2 words, we advanced a little bit the line of research and tightened the gaps in the 2 questions: the existence of upward straight line embedding for paths, and the complexity of deciding whether a straight line embedding exists for certain graphs, meaning for trees in our case. So there are, of course, intriguing open questions left, and first of them is existence of an upward point set embedding for a directed tree to a given general point set and be complete. Do we have to have this additional restriction that we fix where one of the vertices of our tree should go, or we can leave this and the problem still stays hard? And the second question: is it true that every directed path can be embedded in any general point set? So we have many examples of the paths which could be embedded. We don't have yet any example of a path that couldn't. We only have an example of a tree that couldn't be embedded. Thanks a lot for your attention.